Here we have a beam, wooden beam that is created by gluing together 5 pieces of wood. In the center we have one piece of wood, and then we have 4 smaller sections glued into this main section in the middle. We have an external moment loading the structure. The total length of the beam is 5 meters, and we have to calculate the shear stress on the glue areas of this beam. So, the first thing, let's draw here. Let's bring here the formula for shear stress, tau at location Z is equal to V, which is the shear force, internal shear force, multiplied by the S, Z, divided by second moment of inertia, multiplied by the width of the profile at the location of Z. Like that. Alright, first thing we need to do is to do the free body diagram. So, on the left hand side we have FAX, FAY. On the right hand side and here we have moment around that point, 30, like so. The length of the profile this is 1 meter. And this here is 4 meters. So let's do the equilibrium equations first. So equilibrium in horizontal direction is 0. Well, we don't have any other force than the FAX, so FAX equals to 0. Then sum of vertical forces, that has to be also 0 because this is an equilibrium. FAY plus FBY is 0. And the third equation which we have is the sum of all moments must be equal to 0. We will do this around point A, like so. So we have, to the negative direction, we have 30 kilonewton meters. And then to positive direction, we have 5 meters times FBY. And this one has to be 0. Equations 1, 2, and 3. Now, from equation number 3, we can solve what is FBY. It is (30 kN) divided by 5 meters, which will be 6 kilonewtons. And then from equation 2, we can solve that FAY plus 6 kilonewtons equals to 0. So FAY is minus 6 kilonewtons, like that. So now we have solved all the support reaction. We know now all the forces in this structure. Next step is to draw again the free body diagram. And in this diagram we now put the forces that we just solved. here we have, so our FAY was -6, which means that at our first diagram we drew it the wrong direction, so it has to be pointing downwards. So this is now 6 kilonewtons this direction. In here we have 30 kilonewton meters, and in here we have upwards pointing 6 kilonewtons. Next thing which we do is that we must draw the shear force diagram, because we're gonna need the shear force to calculate we are gonna need the internal shear force to calculate the shear force caused by between the layers, caused by bending. So here we have at beginning we have external force pointing downwards, which means that the internal shear force will be to the opposite direction, which is towards the negative direction. We also know that external bending load does not affect the shear force, which means that our internal shear force will be -6 kilonewtons all the way through, like that. So that is our shear force within the material. Now, once we have done that, we can proceed to the next step, which is calculating the shear at the glue areas. So I will draw here the profile. It's like this. So now there are two different ways how you can calculate the second moment of inertia for this profile. You remember I just explained to you briefly some time ago how to calculate it using the subtraction method. We're gonna do it both ways. So let's start it by doing the Steiner method here. So parallel axis theorem method here. So I'm gonna divide this into 5 different sections. This is area 1, area 2, 2, area 3, area 4, and area 5. So how we calculate the second moment of inertia? In this case, because the profile is symmetric to both directions, we know that the neutral axis of this profile is at the middle, so we don't have to solve this one like we quite often have to do. So in this case we don't have to solve it, so we already know it, so we can straight away proceed to calculating the IY. So first let's do the center section. So that is now 100 millimeters wide. So this distance here, this is 100. This is 20. Let's take a look from here. Yeah, 20. This here is 40, like that one. So it's 100 times, area 1 is 100 times 20 power to 3 divided by 12. So now, since the center or the neutral axis of area 1 is at the center of the profile, it is located at the neutral axis of the entire profile, it means that we do not have to add here any Steiner term. So that is the part of area 1, and then we have to add here the second moment of inertia of these rest of these areas, and since all of them are symmetrically located, what we can simply do is that we can have here 4 times what those are, and those are 20 millimeters wide, they are 40 millimeters high, power to 3 divided by 12, and then we have to add here the standard term, which is area, not multiplied plus area, times the distance from the neutral axis of these areas. So the neutral axis to the neutral axis of entire profile, and that distance there, it is 30. And that value we power to 2. And when we calculate this, we will get the alternative way to calculate this one, or we can calculate this IY also this way. So we first calculate what would be the second moment of inertia of this profile if it was complete solid rectangle. So it would be 100 millimeters width of 100 millimeters. The height would also be 100 millimeters, power to 3 divided by 12. And then we would reduce from here these areas. Okay, so this would be alternative way. So we would be reducing these areas, which would be 2 times they are 60 millimeters wide. They are 40 millimeters tall. And then we would add here the standard term, which is area multiplied by the distance from neutral axis to neutral axis of the entire profile, which is the same 30 which was previously, and that one power to 2. And when we calculate this one, what we get is exactly the same result as before, 33.7. Okay, so now that we know the second moment of inertia of this profile, we can proceed to calculate what is the shear stress at the locations of the glue. So let's draw again the shape in here. So our profile is like this. And now what we want to do is that we want to calculate the shearing along these glue lines here. So let's calculate that this area, A2, shears off. The location of center point of area 2 is here. The distance from there to the neutral axis of the profile is like that. The distance is now -10. So we have two distances here. That is the distance to the center of the area, and then we have this distance here, and that is the z value, and that is -10, right? So shear stress at -10 is 6 times 10 to the power 3 newtons. This was the internal shear that we just calculated earlier in this task, multiplied by the SZ value, which is the shearing area, which is 40 millimeters by 20 millimeters, multiplied by the distance from the neutral axis to the neutral axis of the shearing area, which in this case is 30 millimeters. And all this we will divide by second moment of inertia of the profile in bending, 33.7, 10 to the power 5. Multiplied by the length of the shearing area, which in this case is 20 millimeters. And the result which we will get from this calculation is 2.1 like that. So that's how we can calculate the shearing caused by bending loads.